Hello, AP Chemistry students. We're now at section 1.7 on periodic trends. This slideshow is a little bit long, so I'm probably going to break this up into two videos. But our learning objective for this one is to explain the relationship between trends and atomic properties of elements and electronic structure and periodicity. So speaking of periodicity, what does the periodic part of a periodic table mean? Well, the technical definition of periodic means to appear or occur at intervals. And when we say intervals, we mean set amounts of time or a space. So you could say that the concept of January is periodic because if you're in January and you wait an interval of a year, you'll end up in January again. And even though they're at different points in a timeline, they might have some similar properties. Say like where you're at the weather in January is similar from year to year. So that is a periodic property. So the periods or the intervals on the periodic table are the horizontal rows. As you go from left to right, you're going through a full cycle. The periodic table itself is meant to be read left to right, top to bottom. So as you go across, it's kind of like finishing a line, and then you go down to the next one, and you end up at the next period, the next repeating interval. And you could say that things in a period, or sorry, things in a column are where you're like lining up in that interval again. It's kind of like being in subsequent Januaries. You start at lithium, you go through the full cycle, and then you end up at sodium. And even though they're different elements, they're going to have similar properties. And this is true for all of the columns. That's why we call them groups or families, because everything within a column is going to have similar properties. Things within a period aren't necessarily going to share a lot of chemical or physical properties. They will share the physical properties in the sense that like the things on the left side of the periodic table are metals. So like things in a row on the left side are all going to be metals, and then things in a row on the right side are all going to be non-metals. And then also as you go like from one to the next, you're only increasing by one proton and one electron and like a handful of neutrons. So their size and their mass are going to be similar, but overall there aren't a lot of trends and similarities between things in a period. However, in a group, we do end up sharing similar properties. And this is largely due to having the same number of valence electrons. So if we use the alkaline metals as an example, they all have one valence electron in an s subshell. And that's going to make them chemically similar because they all have one electron to work with when it comes to reactions between elements. So the fact that there are sort of repeating patterns on the periodic table, we can look for trends that help us predict similarities and differences between elements. And I specify that we're doing this in the absence of data. We want to be able to just look at the periodic table and then choose two random elements and kind of figure out how they're going to be similar and how they're going to be different. And the properties that we're going to be focusing on here are ionization energy, which we've talked about before, is the energy needed to pull an electron off of an atom. And we're usually talking about a valence shell electron, because those are the ones that require the least amount of energy to pull off. And also ionization energy tells us a lot about the reactivity of an element. Then we're also looking at atomic or ionic radii. This is going to be the size of the atom. And this is defined by the distance between the center of the nucleus and the edge of the electron cloud. I kind of gave the example before of like an atom being sort of like a marble in a football field, where the marble is the nucleus and the football field is the electron cloud, where most of the mass is contained in that center. But then we have this very like large volume of space that the electron can occupy. The edge of that football field to the center of the marble is kind of what we're calling our atomic radii. And we're also going to be looking at ionic radii, what happens to the cloud when electrons are either removed or added. And speaking of removing or adding electrons, we're also going to be looking at the electron affinity and the electronegativity, which are sort of two sides of the same coin that are talking about electrons being added to an atom, where the electron affinity is describing the amount of energy released during that process, and the electronegativity being just sort of a descriptor of how likely that is to occur in the first place, the tendency of an atom to attract electrons. So let's start with talking about ionization energy trends. So we talked a bit before about how ionization energy is related to Coulomb's law. If we have an electron in an orbital, the amount of energy that we're going to need to pull it off is going to be due to the amount of force that's attracting it from the center. And Coulomb's law describes this in the sense of the force of attraction is equal to the charges of the two particles divided by the square of the distance. So the greater the charge, the more attraction. the further the distance, the weaker the attraction. And the weaker the attraction, the less energy is needed to overcome that attraction. So when we're looking for trends with ionization energy on the periodic table, there are two main things we need to consider, which are both related to Coulomb's law. First being the distance of that electron from the nucleus, and then also the effective nuclear charge, which is sort of an abstract descriptor of the relative pull of the nucleus, how strongly the nucleus is attracting electrons towards it. So if we consider the first three elements in the first group on the periodic table, being hydrogen, lithium, and sodium, they all have a single valence electron. We can see that in these Bohr diagrams. However, as we go from hydrogen to lithium, we're now gaining an energy shell because we're going down to another period, and we're getting a new energy shell of electrons. And as we go from lithium to sodium, we're gaining yet another. So that means that as we go down, the furthest away electron, that valence electron, is getting further and further away from the nucleus, which means that the force acting on that electron is going down, and therefore our ionization energy is also going down. So as we go from top to bottom, we see a decreasing trend of ionization energy. And this is probably obvious, but as you go from bottom to top, we see an increasing amount of ionization energy. And this is sort of further impacted by the influence of shielding electrons, because there's that attractive pull of the nucleus, but every time we add a shell of electrons, we're sort of adding a barrier between the nucleus and that valence electron. And we're adding a barrier made out of also electrons, which are going to repel each other. So the more shielding electrons there are, the more shells of inner electrons, the more that force on the outer shell electron is going to weaken. And if we compare hydrogen, lithium, and sodium again, hydrogen has 0 valence electrons because it has no inner shells. Lithium has 2, and sodium has 10 because it has 2 in the first shell and 8 in the second. So if we're considering the trends for ionization energy across the table, now we need to start talking about the effective nuclear charge. And this is actually a value that you can calculate that sort of describes the balance between the pull of the nucleus and the repulsive effect of these shielding electrons. So if we take the number of protons of that element and then subtract the number of shielding electrons, we get a number that sort of abstractly describes how many protons a valence electron is feeling the full pull of. So for an example of that, let's compare the elements lithium, beryllium, and boron, which are the first three in the second row. For lithium, we have 3 protons and 2 shielding electrons, which means we have an effective nuclear charge of 1, which is kind of like saying the valence electron in lithium is feeling the full pull of a single electron. Now, if we're going to go to beryllium, now we're adding a proton, but we're keeping the amount of shielding electrons the same because the amount of core shell electrons are the same. So now it's 4 minus 2, which equals 2. And that means that we're feeling the pull of about 2 protons in the center of beryllium. That means that the valence electron of beryllium is going to be feeling a stronger pull to the nucleus than the valence electrons for lithium. And as we go one more to boron, we increase the proton number by 1, the shielding electrons stay the same, and now we're feeling the full pull of 3 protons. So as we go from left to right, the pull of the nucleus is increasing. So that means that the ionization energy is going to be increasing because it's going to be harder and harder to pull electrons off of it when the strength of that nucleus is increasing. So overall, the trend here is as we go from left to right, we're increasing in our effective nuclear charge, which is overall increasing our ionization energy. So the overall trends from bottom to top, we're increasing in ionization energy, and from left to right, we're increasing in ionization energy. And sort of by proxy, as we're going diagonal to the top right side of the periodic table, we are increasing in ionization energy. Fluorine being one of the most hardest to ionize elements. We kind of ignore the noble gases because they often don't get ionized just because the pull of the nucleus is so strong. All right, so now let's talk about the atomic radii, the general size of the atoms. So the trends for this are going to be sort of explained by the same thing as the trends for the ionization energy, because the size of that electron cloud is going to be heavily influenced by how much the protons are sort of pulling on it, and then how much the inner shell electrons are sort of repelling it outwards. So there's a balance of like push and pull, where the electrons are being pulled towards the center by the nucleus, and then also pushed outwards by the inner shell electrons. It's really similar to an idea in physics when we look at the sort of stabilization of a star. A star is going to have a really big mass, which means it's going to have a lot of gravity that's kind of pulling the mass towards the center. But then also you're having nuclear fusion, where atoms are crashing into each other and releasing a bunch of energy that has this explosive force that pushes matter outwards. So there's a balance between the outward push of explosion and then also the inward pull of gravity. And that generally sort of keeps it at a stable volume. Of course, there are stages of a star. It goes through different parts of its life cycle where the size changes, but in any one stage of its life, it's holding itself steady based off of this balance. And the sort of atomic size is similar, where we have the pull of the nucleus and then the push of the shielding electrons. So let's consider lithium and sodium. So for lithium and sodium, if we calculate their shielding electrons, if we calculate the relative amount of attractive force of the nucleus, we see that for lithium, we have 3 protons minus 2 shielding electrons. We get an effective nuclear charge of 1. For sodium, we have 11 protons and 10 shielding electrons. We also have 1. So we usually find that the effective nuclear charge of things in a column are going to be the same. So if we're going to figure out how the size is being affected here, all we have to do is just really consider the electronic structure. Since the relative pull of the nucleus isn't really increasing as we go down, we consider the electrons. And as we go through each row and get to a new row, we're adding a new shell. So that means that the electrons are getting further and further away from the nucleus, and we're getting more and more shielding electrons in between. So you can imagine as it's starting to swell because we're adding more and more electrons to it that are starting to repel each other outwards. So that means as you go down a group, we're going to be increasing in our atomic radius. And we're going from left to right, you might assume that the size is going to increase because the mass is going to increase. Like neon has a lot more protons than lithium does. But what we actually find is that the size decreases as you go from left to right. And this is due to that effective nuclear charge again, because we have the same number of shells of electrons, so we're not increasing in the amount of shielding electrons. So the amount of push outwards is not increasing, but the amount of pull inwards is. As we go from lithium to beryllium, we saw we get more protons and a stronger pull on the nucleus. And that sort of shrinks the shell or shrinks the atom down as that outer shell is being pulled closer and closer to the nucleus due to that higher charge. So for ions, it's going to be based off of how many electrons it's gaining or losing. So the 2 types of ions are cations and anions. So either positive ions, where we have a loss of electrons, or anions, where we have a gain of electrons. And we need to consider how the electron cloud is going to be affected by this loss or gain. If you think about like taking things away or adding to a cloud, that might be kind of obvious that when you pull electrons away, the size is going to decrease. But when you add electrons to the cloud is going to increase. And this is largely due to the repulsive effect of the electrons again. If you're pulling away things that are repelling each other, it's going to shrink down. If you're adding things that are going to repel, it's going to start to swell more and get bigger. So in general, cations of an element are going to be smaller than their neutral forms. So you see here that this lithium plus ion is much smaller in size than the neutral lithium because it lost electrons. However, for anions, as we add electrons to the cloud, we can see that the cloud gets bigger. So as sort of a practice of this, let's consider 3 isoelectronic atoms, bromine, argon, and rubidium. So we have a bromine anion, we have neutral argon, and then we have positive rubidium ion. And we want to figure out which of these has the largest radius and which one is going to have the smallest. And if you recall, isoelectronic means they all have the same number of electrons. When bromine gains 1 electron, it's going to be similar to argon. When rubidium loses 1 electron, it's also going to be similar to argon in terms of the total number of electrons available to it. So they all have the same number of electrons. They all have the same amount of full subshells. So what we need to consider here now is the charge of the nucleus. So they all have the same number of electrons. So the repelling the repelling energy is the same, but rubidium is going to have the most protons in its nucleus. So therefore, it's going to have more pull. It's going to have more. The balance is going to be heavily leaning towards the pull rather than the push. Whereas bromine has the least number of protons of the three, and it's going to have the weakest pull. So we can say that the bromine is going to have the largest radius because its electrons are being pulled in less than argon, and then rubidium is going to be the smallest because it has the most amount of protons and therefore the strongest pull towards the center. So it's going to shrink the most. And I'm going to break here for now, and we'll talk about the other bits in the next video.